This is part one of what will probably be two-part lecture, two parts on redox reactions or oxidation reduction reactions. We generally just use the shortcut redox because it's much easier. Let's go to the slides. This slide set is in module 8, and it's the 8D redox chemistry. Very simply, redox reactions, oxidation reduction reactions, are an exchange of electrons. When you have acid and base, that is an exchange of protons. Redox reactions, we are exchanging electrons. And it can be very complex. There's another topic you can entire lifetime studying. We're going to keep it simple. We're not going to get too deep into it, but it involves a transfer of electrons, and we know what's happening by assigning something called an oxidation number. And again, it's actually very straightforward. So you're going to learn to assign oxidation numbers. You're going to learn to determine if a reaction is a redox or not. That's actually super simple. In every redox reaction, you have a reactant. So on the left side, you have a reactant that's oxidized, and you have one which is reduced, because in this exchange of electrons, one of them is giving the electron up. Well, the other one has to be receiving it. So you have, just like an acid base, you have a donor and an acceptor of a proton. Here you have the donor and the acceptor of electrons. And so you can identify them, and then the next lecture we'll talk about the activity table and if a redox reaction will occur. The most important thing to remember about oxidation numbers is it's all bookkeeping. You assign your oxidation numbers at the beginning. You assign them on the product side. You look at the difference and you say, did the oxidation number change? If the oxidation number changed, you have a redox reaction. If the oxidation number did not change between left and right, you don't. It's that simple. So determining if something is a redox or not, you assign oxidation numbers left and right, and there are very simple rules for that. And you look at the left and right, and you say, is there a change? Reduction is the gain of electrons. Oxidation is the loss of electrons. Zinc, one of the rules that you will learn will show you that when you have a pure element all by itself, and it doesn't matter if it's a diatomic, this could be oxygen gas, O2, nitrogen gas, a single element, it doesn't matter. If it's just a pure element, it's always zero. Simple rule, one of the easiest ways you can tell if you have a redox or not. Because if it's now on the other side, that same element is now either an ion or within an ionic compound, you have a redox. Because anytime your pure element becomes ionized, it has just, in this case, this zinc, lost 2 electrons, right? It's a 2+ ion because it has 2 more protons than electrons, where here they were balanced, because it lost 2 electrons. So it lost electrons, therefore it was oxidized. This copper starts out with a 2+ oxidation number because anytime you have a simple ion, your oxidation number is the ionic charge. So those are the 2 simplest rules we have. And the other ones aren't that much more complicated. So you have an ion, a simple ion. Your oxidation number of this copper is 2+ because it's the ionic charge. Over here, your copper is a pure element, just copper. Therefore, it's 0. It's kind of in a perfect state. So you went from a +2 to a 0, you gained 2 electrons, 2+ and 2- to get to the 0. So therefore, when you gain electrons, you are reduced. So zinc threw its electrons and copper caught them. You always have a pair in a redox reaction. So some of the examples, when we have plating, you've heard about silver plating, rust. these are redox reactions. I don't know if you'll get a chance to do this in the lab this fall. I hope so. This is a really fun one, the redox reaction. And you actually plate, you put the metal in a solution with ions. And so if we go back, so okay, here's the reaction equation again. So zinc metal and copper ions. So this is a copper nitrate solution. Copper exists in the solution as ions. You will get a reaction that takes place. The copper is going to swipe the electrons from the zinc, and so it's going to become solid copper. Well, where's that solid copper going to go? It's going to go on the surface of the zinc. You see, you get this little fine line, this entire, at the end of the reaction, this entire surface of zinc will be coated with copper metal, and the zinc that gives its electrons up will become ionized and will be floating around in the solution as zinc ions. Now, one thing about redox reactions, they can only go in one direction. So zinc solid and copper ion will react, but the reverse will not happen. You do not have reversible reactions with the redox. It's one direction only. And you're going to learn how to tell that, how to predict that. So, exchange of electrons. You will learn to assign oxidation numbers, and that will tell you. You look on the one side, you look at the other. If there was a change in oxidation number, you have redox. It is that simple. If they're the same left and right, you don't. Keep in mind, redox oxidation numbers are assigned to the individual element, the individual atom or ion. Zinc has an oxidation number. Copper. If you have a molecule or an ion, let me see if we have an example one here. You still, and these are you'll learn these rules, you assign the oxidation number to the individual atom, and it's for the individual single. So the oxidation number of nitrogen, the single nitrogen, the oxidation number of each hydrogen atom, all right? So the oxidation number is for the individual atom, and each of those atoms will have the same oxidation number. So there are a couple of ways to remember which is oxidized and which is reduced. And I still use them. I have to write it down every time. I learned Leo says, the lion says gur. Let's go to the whiteboard a minute. Other people learned oil rig. Oops, forgot to adjust this. So I learned Leo, the lion says gur. And it may sound silly, but you know what? It works. And that's what matters. Let me get this to focus. Let's try that again. There we go. Okay. Leo says gur. And the other one that I have heard of, okay. So the one I learned, Leo, the lion says gur. So lose electrons is oxidation. Oxidation or oxidized. Okay. Gain electrons, it's reduced or reduction. The oil rig is oxidation is losing. And then reduction is gaining. So whichever one works, it really helps, because it is the biggest challenge with redox reactions is not getting confused, like a lot of things we learn. So I'm going to stick with what I learned, which was Leo, the lion goes grr. When you lose an electron, so our example was zinc solid plus copper ion. Notice my signs. Zinc, or my phases, zinc is a solid. It's a piece of metal. But my copper is aqueous. It's an ion. It's in solution. The one, if you do the lab, it'll be copper nitrate. And I apologize. Let's start this over a little further to the left. So the example from the slide was zinc solid plus copper. We're not putting the nitrate in because that's a spectator ion. We're only interested in the actual atoms and ions involved in the reaction. So we end up with a zinc 2 plus. Now this is aqueous. This is now in solution. And the copper becomes copper metal. So the simple, and you put oxidation numbers on the top. That's the other thing. So these are the two simplest examples. Anytime you have a pure element, solid copper, solid zinc, hydrogen gas, which is H2, bromine gas, chlorine gas, oxygen gas, carbon, graphite, solid sulfur. It doesn't matter how many of them you have. If you only have one element in your molecule or atom, it's got a 0 oxidation number. There is no unequal distribution of electrons. Back to electrons again. And distribution of electrons. So the zinc is a solid, it's an element, so it's 0, and the copper is a solid, it's 0. The other very simple rule is when you have an ion, your oxidation number, a simple ion, is the charge of that ion. So this is a simple ion, copper 2 plus. And I have to admit, it's easy to get confused about where the plus goes in front or the plus goes behind, because in the ion, it goes after, and then in oxidation number, it goes in front. Now, like everything else, your oxidation numbers have to be balanced at the end. We have a 2 plus on this side, a 2 plus on this side. So what's happening? Copper is stealing 2 electrons. So I've got the arrow going there because it's taking it. But they're going, the 2 electrons, so copper is stealing 2 electrons from zinc. It's like I said, it's like a football. Zinc threw it, copper had to take it. That's why you always have to have a pair in a redox reaction. What do we call that pair? Here's some more terminology. I want my green for some reason. Can't find it. We're going to go with blue. Sorry. So the one that loses electrons is enabling the other reactant to be reduced. By losing these, he's enabled the other reactant to gain electrons, right? Makes sense. This one loses it, this one has to gain it. By gaining, this one is enabling the zinc to lose. So you have a partnership. So the one that loses electrons is being oxidized, and we call it the reducing agent. And it's also called the reducer. So the ending of your terms is critical here. This is oxidation or oxidized. But this is reducing agent or reducer. So you have to make sure you give me the full word. I mean, at least the ending of it. Well, if that's the reducing agent, because it is the agent of allowing this to be reduced. This is the agent that allowed that to be oxidized. So we call it the oxidizing agent. It's enabled this to be oxidized, or the oxidizer. It forced that to be oxidized. So this is where you can start to get confused. And so I actually write all of this down. If we were in the classroom on a big board, I would have that all written down as soon as I started this lecture, including this, and I would refer to it constantly because it's easy to get confused. So if this is the reducing agent, this can be called a conjugate oxidizing agent. But I'll come back to that. But we also, just like with acid base, you have conjugates, you have a pair here, and then you have a reverse pair over here. You have the same thing with redox. So far we have, what's the definition of oxidation and reduction? They're exchanging electrons. How do you know? You calculate the oxidation number at reactants and products, and you say, are they different? If there's a difference, you have a redox reaction. If a reactant loses electrons, we call it oxidation. And we're always looking at the behavior of the reactants because this only goes one way. This cannot go reverse. If your reactant loses electrons, it's called oxidized. Oxidation, or we say it is oxidized. And if it's oxidized, it's a reducing agent or a reducer. The other reactant, therefore, had to gain the electrons. We say that's reduced, or it's reduction. And the reactant that's reduced is acting as an oxidizing agent, or we simply say the oxidizer. Okay. Like I said, I highly recommend you write this down when you start to work your problems, and you write that underneath it. And don't just try to memorize it because it's easy to get confused. But so how do we assign oxidation numbers? And like everything else, we have rules. And remember here, oxidation does not occur without reduction. You have got to have one's giving, one's taking, just like acid base. And as I said, just like acid base, here's some comparisons. For a redox reaction, we have a transfer of electrons, which is a transfer of a negative charge. In the acid base, we have a transfer of protons. And so we are transferring the positive charge. Both situations involve something seeking the lowest energy configuration. Chemistry is always about a reaction happens because your elements are trying to seek the lowest energy configuration or conformation. And so in redox, that occurs with an exchange of electrons, and in acid base, that occurs with an exchange of protons. But they're still looking for the lowest energy, most stable conformation. And just like acid base, oxidation and reduction will always occur together. One of your reactants is the oxidizer, one is the reducer. One is getting reduced, one is getting oxidized. Same for the acid base. And we do have what can be called a conjugate. And I'll get to that. So in this example, you have already, the oxidation numbers have been assigned. They are for the individual atom. So it doesn't matter that you have 3 hydrogens, but the number is for each individual hydrogen. So we look at this question, and the numbers are already assigned. And so you say, is this a redox reaction? Well, my nitrogen is a -3 over here, and it's a -3 over here. No change. My hydrogen is a +1 over here, right? Both of them are +1, and it's a +1 over here. No change. My sulfur is a +6, and it's also a +6. There's no change. And my oxygen is a -2, and each oxygen over here is a -2. There is no change in the oxidation numbers. Therefore, this is not a redox reaction. I'll explain the bottom numbers later. What about this reaction? These both involve ammonia, by the way. So here, nitrogen is a -3 oxidation number. Over here, it's a +5. Well, right there, you know you have a redox reaction. That tells you. It went from a -3 to a +5. So it lost 5 electrons. These three and, no, it lost a lot more than that. It lost 8. So it lost 8 electrons. Where'd they go? Well, my hydrogen is a +1, and it's also a +1 over here, so it didn't go there. My oxygen here is an element. The only thing here is oxygen. So that automatically has a 0 oxidation number. But over here and here, my oxygen is now in molecules, and so it's gained electrons and it's gone to a -2 oxidation number. So each of these oxygens has gained 2 electrons. So you have a loss of electrons from the nitrogen and a gain of electrons from the oxygen. You have a redox reaction. The nitrogen lost electrons and therefore it was oxidized, LEO, lose electrons, oxidize. If it lost and was oxidized, then oxygen had to have gained and been reduced. Once you determine that's the other one that changed. So the oxidizing agent causes the other guys to be oxidized. It's the agent of change for the other reactants. A reducing agent causes the other guy to get reduced. It's the agent of change for the other reactant. I don't know why that's. Okay. So we assign oxidation numbers. When the oxidation number increases, becomes more positive, we've lost electrons. So if you go from a -3 to a 0, you've become more positive. You look at the timeline, I'm sorry, the number line. Back here, there. You look at the number line. Moving to the right becomes more positive. So if your number starts out on the negative and it ends up as 0 or a positive, you are going to the right, you are going more positive, and it is an oxidation reaction, or it's being oxidized. If your oxidation number from left side to right side, reacting to the product, becomes more negative, you start out as a positive or 0, and you move more towards the negative side of the number, bring this one blank, the number scale, it is being reduced, it's gaining electrons, we say it becomes more negative. So sometimes we call it oxidation numbers. You will also hear it called oxidation states. And we have rules that we follow. Now, let me see, do I have him? No, I don't have the link in here. So there are two kind of set of rules. There's a hierarchy, and the first 3, if you have to choose between one of the first 3 or one of the later rules, these rules, these take higher priority. So for an atom in its elemental form, the oxidation number will be 0, right? And for a monatomic ion, a simple ion, it's the ionic charge. The rest of them, you have to do the bookkeeping. You have to do simple math to add up the oxidation numbers of the known and the unknown. By that, I mean there are some that will always come into play. And then here's our hierarchy. The lower the rule is, you choose the rule above it if you have to make a choice. So for group 1A, not including hydrogen. So lithium, sodium, potassium, rubidium, cesium, your oxidation number will always be +1. And group 2A, beryllium, magnesium, calcium, strontium, barium, they'll always be +2. So you will be able to assign that oxidation number anytime you see those, because it's a set rule. In hydrogen, it depends on what it's with. If it's with it, because it has to, the sign has to change based on what it's with. So if it's in with a non-metal, your non-metals are going to be more negative. It's a +1. So hydrogen sulfide, your hydrogen is going to be a +1. But if it's in with metals, magnesium or potassium or sodium or calcium, it's a -1. Most of what you're going to come across is going to be with nonmetals. But if you see hydrogen with metal, it's a -1. Fluorine is -1 in combinations with metals and boron. Pretty much all the fluorine you're going to get is -1. Oxygen, rarely you will see it in a peroxide, which is a -1. 99% of what you're going to see is oxygen has a -2. So most of the time, 99% of what you're going to get this semester is oxygen has a -2 oxidation state. And then group 7A, your halogens, it's usually a -1, but notice how low this rule is in the hierarchy, because the oxygen group rule would have a higher priority. But most of it's very similar to the ions. Most of your halogens, your 7A, are going to have a -1. And they also have a -1 ionic charge. So rule 3 can be applied whenever oxidation numbers have been assigned to all but one element. What is rule 3? Rule 3 is the sum of the oxidation numbers have to add up to the total charge on your molecule ion. Let's say a polyatomic ion. So just like everything else, each individual sum has to equal the whole. I'm going to pause for a minute because Tyler DeWitt has a video I really like. And I was hoping I had it on the slide, but I don't. So I am going to pause and find. Okay, so I found the video. It's 13 minutes long. I'm not going to play the whole thing, but I am going to play the beginning of it. And his written set of rules is super useful. In the class, I printed out and I handed out to the students for their reference because it just makes it really clear. So pay particular attention to his rules. I'll pause it when I get there. So it's how to calculate oxidation numbers, Tyler DeWitt, YouTube it. And actually, let me just, do you see this? This is an excellent description of the rules. The rules I just read out, here they are, and just this really simple, easy to understand format. So I highly encourage it. So let's listen to him explain oxidation numbers for a few minutes.
Oxidation numbers for the different elements in a chemical compound. The oxidation numbers are the numbers that I've written here above each one of the elements. Now, if you want to learn more about what oxidation numbers are or why they're important, check out my video called What Are Oxidation Numbers? In this video, we're going to work through the process of how you figure out what these numbers are. So here are the rules that we're going to use to figure out oxidation numbers. Now, just so you know, every teacher and textbook has their own version of these rules, but they all work in pretty much the same way. So if you learn mine, you'll still get the answer right 100% of the time, even if these are a little bit different from your teachers. I'm going to talk through a few of these rules right now, and then I'll introduce the rest just as we work through practice problems. The first is this. oxidation number of 0. Here's what I mean by that. There are a lot of chemical compounds that have just one element. That element is not combined with any other elements. That's what I'm calling an element by itself. So that's something like Cl2. It doesn't matter how many atoms of that element you have, just as long as it's only that element and none others. So Cl2, an element by itself, oxidation number of 0. Sodium, Na, by itself, 0. S6, just sulfur, nothing else. P4, phosphorus, and nothing else, 0. So that's probably the easiest rule here. It's always 0 for the oxidation state if you have an element by itself with nothing else. The other rule here is about monatomic ions. These are ions that are made of only one atom. So like this. For monatomic ions, their oxidation number is the same as their ion charge. So for K plus here, its oxidation number is going to be plus 1. For N3 minus, it'll have an oxidation number of minus 3. And Mg2 plus here is going to have an oxidation number of plus 2. Now keep this in mind. When we write oxidation numbers, we write the sign first. So plus, minus, and then the number after. This is the opposite of how we write ionic charges. So just keep that in mind. The charge might be 2 plus on magnesium, but the oxidation number is plus 2. Now for the rest of these rules, we usually use more than one together. So I'll just talk about these as we use them in example problems. Here is our first example. KCl, we want to figure out the oxidation numbers of the elements in this compound. Okay, so let's take a look at our rules here. K, potassium, is in this column in the periodic table. It's in group 1A. So there's this rule that elements in group 1A are always plus 1. So that is potassium's oxidation number. Then we have Cl over here. That is one of the halogens. Halogens, usually minus 1, positive with oxygen. Well, Cl certainly isn't with oxygen here, so we'll give it a minus 1 oxidation number. Now, I want to use this to show you a third rule. That's this rule right here. The sum of oxidation numbers for a neutral compound equals 0. KCl is a neutral compound here. It doesn't have a charge after it. So that means that the sum of these oxidation numbers is going to equal 0. And that's definitely true here. Plus 1 minus 1 equals 0. We'll use this later on when we do other examples, but just keep that in mind. The sum of oxidation numbers for a neutral compound should always equal 0. MgO. Mg is in this column in the periodic table, group 2A. And group 2A elements are always plus 2. So there's that. Oxygen here, we have a rule for oxygen. It is usually minus 2. It is minus 1 in peroxide. H2O2 hydrogen peroxide is the most common peroxide. It's probably the only one you'll ever see. But anyway, this oxygen is definitely not in hydrogen peroxide, so it's fair to say that its oxidation number will be minus 2. Plus 2 for Mg, minus 2 for O, and they add together to make 0 because this is a neutral compound. CO, carbon monoxide. Let's figure this one out. Okay, so C here, there isn't any rule for carbon. So we'll have to figure it out based on what we do know. Okay, so we do know oxygen. Oxygen is usually minus 2, unless we're in a peroxide. Definitely not a peroxide. So we can safely say that oxygen's oxidation number is minus 2. Now, let's use this other piece of information that we know, and that's the sum of oxidation numbers for a neutral compound should equal 0. So whatever carbon's oxidation number is should add together with oxygen's to make 0. So we can figure out that carbon's oxidation number should be plus 2. Minus 2 from oxygen gives us 0. NH3. Okay. N, there isn't any information about that. So just like in the last example, we'll have to figure out its oxidation number using what we do know. Here we've got hydrogen. There's a rule for hydrogen. Hydrogen is plus 1 with nonmetals and minus 1 with metals. So nitrogen is definitely a nonmetal, which means that in this case, hydrogen is going to have a +1 oxidation number. Okay, but there are 3 hydrogens. Each one of them has a +1. So what we have to do is we have to multiply this +1 times 3 for the 3 hydrogens, and that's going to give us +3. Now, let's keep this rule in mind, that the sum of oxidation numbers for a neutral compound should equal 0. NH3 is definitely a neutral compound. We don't see any charge here. So, whatever nitrogen's number here is, needs to add together with +3 to make 0. That means the nitrogen here has to be -3. That adds there to get 0. So its oxidation number is -3, hydrogen's is +1. CaC2. So calcium here is in this column, group 2A, so we know that its number is always +2. We don't know what carbon's number is, but we can figure it out. What we do know is that calcium's number plus whatever carbon's number is needs to equal 0 because this is a neutral compound. It doesn't have a charge. That means that the total number on carbon is going to be -2. But there are 2 carbons here, so we have to divide this number between the 2 of them. So we're going to take this and divide it by 2 to get an oxidation number of -1 for each one, +2 for calcium, -1 for carbon. NO2 1-, check this out, it is an ion. So this is going to be a little bit different. In this case, the sum of oxidation numbers for a polyatomic ion equals the ion charge. So let's see how we'll use that here. Nitrogen, we don't know what its oxidation number is going to be, but oxygen here is usually -2. So we have -2 here, but we have 2 oxygens. So we're going to do -2 times 2 is going to give us -4 altogether. Now, whatever nitrogen's is, when we combine it with -4, we need to get not 0, but we need to get -1, because that's what the ion charge of NO2 1- is. So this means that we will have 3 plus 3 plus 3 minus 4 gives us -1, which means that the oxidation number here on nitrogen is going to be +3. HNO3. Okay, let's take a look at the rules. We got hydrogen. Hydrogen here is combined with nonmetals, nitrogen and oxygen. So that means that its oxidation number is going to be +1. Oxygen over here is going to be -2, but we have 3 oxygens. So we got to take this -2 times 3 to get -6. Okay, so now we have +1 from the hydrogen plus whatever nitrogen is. -6 has got to give us 0 because this is a neutral compound here. So that means that in this case, nitrogen's oxidation number will be +5. 1 plus 5 minus 6 equals 0. Now I'm going to start talking about some more challenging examples that use some rules here that are a little less common. ZnH2. Okay, zinc here, we don't know what its charge will be, but hydrogen, we have a rule for that. Now we've been used to hydrogen's number being +1 because it's been with non-metals, but here.
Okay, I'm just going to, I'll go ahead and play the rest of this because we're at 10 minutes and it's really an excellent video, but the whole thing is 13 minutes, 25 seconds. If you want to pause, fast forward, whatever. Okay, so back to Tyler.
It's with a metal, with zinc. So that means that its oxidation number is going to be -1. But we have 2 of these hydrogens, so it's going to be -1 times 2 give us -2. Since this is a neutral compound, whatever zinc is plus -2 has to give us 0. So that means that zinc's oxidation number must be +2 here. So we got +2 for zinc and -1 for hydrogen, because hydrogen is with metal, so it has a -1 oxidation. BrO3 minus. This is a tricky one, but it's pretty common. So Br, bromine, is one of the halogens. The rule for the halogens is they are usually -1, but they are positive with oxygen. So I'm not going to put 1 minus in here because it's with oxygen. So let's go to oxygen instead. Oxygen is usually -2 since it's not peroxide. So let me put that here. -2. Now we have 3 oxygens. So that's going to be times 3 to give us -6. Now whatever bromine is, -6 has got to give us -1 because this whole thing is a polyatomic ion that has a charge of -1. So that means that bromine's charge must be +5. +5 -6 gives us -1. So this is an exception where the halogens, instead of having an oxidation number of -1, have a positive oxidation number because they're paired up with oxygen. Keep that in mind. ClF3. Okay, so here we have 2 halogens in the same compound. We have fluorine and chlorine. How are we going to figure this out? Well, this is one of these things that sometimes happens where fluorine combines with another one of the halogens. We're going to zero in on this rule first, that fluorine is always, always, always -1. So I'm going to put a -1 right there, multiply it by 3 because I have 3 of them, and get -3. Now chlorine, the other halogen, says that these other halogens are usually -1, but not always. They can be positive with oxygen, they can also be positive with fluorine here. So fluorine gives us -3, chlorine must be +3, so that these can add together to give us 0, since this is a neutral compound, which means that chlorine's oxidation number must be +3. And it's +3 instead of -1 because it's paired with fluorine, which is always, always, always -1 no matter what. So that's how to work through these rules to figure out what the oxidation numbers of elements are in a compound. If you want a little bit more practice, I'm going to have another video with more practice problems. If you just are a little bit shaky on this, doing more and more practice problems is the best way to get good really fast.
Okay, so you can see that's a really excellent video, and his rules are just so nice and simple to follow that I recommend using his rules if you have a way to screenshot them or print them or put them on your phone or something. So I'm actually going to stop here setting up the rules. The next lecture portion will be, part 2 will be, I'm going to work out problems. We'll work out, the oxidation number problems and also writing redox reactions. So this is the end of part 1 of the redox lecture, and it looks like that we're going to have 3 parts to this.